Now, sum of products is also a word for a form of equation. We use the sum of products method to make a Boolean expression, and that Boolean expression came out in sum of products form. Sum of products form looks like this, etc. And some of these might be inverted, and there are ors between them. So you're looking at a lot of products or and gates and ORed together. And again, it's beyond the scope of the course to prove why this works and why this is a Boolean expression that represents a truth table that has an output of 1. But I did post a document called Practice Problems, Sum of Products, that does give you the explanation of why this works. So here are some other examples of sum of product form. You don't have to have all 3 factors in each of the expressions. So even this is sum of products form, or this is sum of products form, or this is sum of products form. So as long as you're seeing products separated by sums, it's sum of products form. So products separated by sums, sum of products form. Here we have products. Here are all the products separated by sums, sum of products form. Here's the sums. Here are the products, sum of product form. So let's do some examples where we just need to put things in sum of products form. And I just want to highlight this for you in that in a sum of products form, a single overbar cannot extend over more than one variable. So that's important as well. So let's look at these examples. And you see here, this bar, this inversion bar, is over more than one variable. So this is not in sum of products form. So this example is asking me to convert the following expressions into sum of products form. So let's do that. Here, I notice that this looks like sum of products form, but then over here, this is not in sum of products form. But all I would have to do is expand this. So what I'm doing is I'm just expanding across the brackets, keeping it in alphabetical order. And now I have my products and the sums. This is sum of product form. That's all there is to it. That is in sum of product form. This one needs to be expanded as well. Here I need to expand the A terms, then I need to expand the B across. Keeping in alphabetical order. Noting here, there are 2 B's, and I remember that that is a theorem, and I'm just over here, I just reminded myself that that means B and B. So I look at an AND gate, and I recognize that, well, if the B's are both zeros, the output's 0. If the B's are both ones, the output's 1. So therefore, the output must be the same as each of those inputs. So therefore, BB can just be simplified as B. So this simplified expression looks like this. And I don't really see a purpose of simplifying this further. I think this is as simple as this expression can get. And if I look at question C here, I do see that I can do De Morgan's. And remember to start with your innermost brackets first. So I'm going to do De Morgan's in this innermost bracket. And I'm going to change the sign. And if I change the sign, I can break up this inversion. Keep that in a bracket. Keep the rest of the expression the same. And then my next step is to now break up the next inversion where one of the terms is literally this big expression and the other one is just C. I need to change the sign, and that means I can break up this overbar, this inversion. And now I see that I can do De Morgan's again in here. So I have the NA bar and I have a C bar and I have to change the sign, therefore I can break up the inversion. I'm going to carry along these brackets. Now I think we called it theorem 18 where I have 2 bars of equal length, so that's equivalent to just A itself. I might as well just keep this bracket. And now I realize that I'm just double checking my work here, make sure I did this right. Just going to make sure I did this right. So I broke up this big bar. I changed the sign. I broke up the bar. And then I broke up this big bar by changing the sign and breaking it up. Then I broke up this bar by changing the sign and breaking it up. And then I realized that I can get rid of the double inversions. So I'm left with this. And so now that's the same as writing C bar times A plus C. Turns out the brackets were important. And now I can expand that. Plus C bar C. Now let's think about C bar C. That means that's an AND gate. And I can look back up here. That's this and this because one of them is 0, one of them's a 1, and one of them's a 1, one of them's a 0. So the output must be 0. So this goes to 0. So this is AC bar plus 0 or 0. Let's look at an OR gate again. The inputs of an OR gate. The outputs of an OR gate say the output is high if one or the other or both are high. And so when you're ORing anything with a 0, then the output here I'm looking at, here's the 0 I'm ORing with. So the output depends on this input. It's going to be the same as this input. So the output is the same as the input, which means that all of this goes to a C bar equals a C bar. And this is described as one of our theorems. So this this expression, this is a nice simplification problem, and it also is not in sum of products form until we got to here. That is sum of products form. But I didn't like it because it could be simplified further. This is also sum of products form. So this is the final answer. So that's a few examples of sum of products form, which is a form that comes out of sum of products design method.